Hey everyone, and welcome. Today we're diving into a pretty wild idea from the world of physics. It's one of those questions that's so fundamental, it could totally shift how we think about the fabric of reality itself. So think about this for a second. We tend to imagine the universe as being, well, pretty straightforward, right? But what if it's not? What if on some deep, invisible level, space-time itself is actually twisted? Now, this isn't just some sci-fi concept. It's a real question that physicists are asking. And you know what? They've come up with a really clever way to try and find the answer. To really wrap our heads around this, we need to talk about something called non-orientable topology. The best way to picture it is with a good old Mobius strip. You take a strip of paper, give it a half twist, and tape the ends together. If you imagine an ant walking along it, it can go all the way around and end up right back where it started, but now it's upside down, on the other side, without ever crossing an edge. That's because there is no other side. So the big question is, could space-time have a property like that? Okay, so you've got this mind-bending idea for mathematics, but how do you take something like that and turn it into real-world physics, something that could actually have a measurable effect on the universe? Let's break down how they're trying to do just that. First things first, and this is super important, this research isn't trying to throw Einstein out the window. Not at all. It's actually the opposite. The whole idea is to see if they can add one tiny new ingredient, this twist density, into the existing framework of general relativity, and do it in a way that fits perfectly, and, most importantly, can actually be tested. So the theory itself unfolds in four pretty logical steps. First, you just start with the hypothesis. Let's say this twist, which they call rho-cap, is a real thing. Step two, you need a way to describe it. So they use a mathematical tool called a scalar field, which they've named chi. Just think of it like a weather map that, instead of showing temperature, shows you how twisty spacetime is at any given point. Third, you plug this new field right into the standard equations of gravity. And fourth, this is the really smart part, you make sure that this new ingredient doesn't break any of the rules we already know are true. Energy is still conserved, and it doesn't mess with any of the classic gravity tests we've done for decades. All right, so it's a neat theory, but how in the world do you test for a twist in space-time? It's not like you can just build one in the lab. Well, this is where the real genius of this whole project shines through. They figured out a way to create a proxy, a kind of stand-in for space-time that they can actually build right on a tabletop. And this really lays it out perfectly. Trying to poke and prod the topology of actual space-time, yeah, that's impossible with the tech we have today. But creating a custom-made material that mimics the mathematical properties of that twist, that is a brilliant and totally doable workaround. And the key to this workaround is something called a metamaterial. This isn't a material you find in nature. It's something you engineer from the ground up to have very specific, often bizarre properties. In this case, the researchers designed a high-tech circuit board that, from an electromagnetic point of view, behaves as if it has that non-orientable twist built right into its DNA. So let's take a look at the actual device, which they call the Klein cubed stack. It's a custom-made 3-layer circuit board built from some very specific high-performance materials. The secret sauce is what they call controlled orientation reversals. That's the engineered twist we've been talking about. And look at how careful they're being here. They've balanced every single physical property to make sure it's a fair test. They even had the boards made by 2 completely different manufacturers, just to be sure that any results they get aren't some weird fluke from one company's process. That's serious science. Okay, so they've got their space-time proxy. The stage is set. Now, how do they actually listen for the signal? How do they find the evidence of the twist? Well, they have to carefully measure how the board behaves and see if that engineered twist is changing things in a way the theory predicts. The first measurement they're taking is something called the resonant Q factor. That sounds technical, but the analogy is perfect. It's basically like measuring how clearly a bell rings. A really good bell will ring for a long, long time. It has a high Q factor. In this circuit board, they're looking to see if adding more twist has a damping effect on its electromagnetic ring. Does it make the bell sound duller? If it does, that could be a signal. The second measurement is all about heat flow. You know how if you put a drop of water on a piece of wood, it tends to spread out along the grain? That's called anisotropy. Well, they're doing a similar thing here. They hit the board with a pulse of heat and then watch very, very closely how it spreads. The big question is, does the engineered twist create a kind of grain in the material, forcing the heat to spread out unevenly? If so, that would be another huge signal. And what's so cool about this is that it isn't some far-off theoretical project. This is an active plan with a real timeline.
The first 2 weeks are for building the boards and getting the lab ready. Then they've got a month to run all the tests and analyze the data. After that, they take about 90 days to confirm everything in a second lab and then release everything, and I mean everything, to the public. This is what science in action looks like.
Okay, so what happens when all the data is in? This is a really crucial part of the whole story because no matter what they find, whether there's a signal or not, we end up knowing more than when we started. Science moves forward. So let's play this out. There are two basic ways it can go. On one hand, if they find a clear signal, if the Q factor consistently drops or the heat flow changes as they increase the twist, that's huge. It would be the first ever experimental evidence that topology can be a real physical variable. On the other hand, what if they find nothing? What if there's a null result? Well, that's also incredibly useful. It tells them that this specific design didn't work, and they publish that result so that other scientists don't go down the same dead end. Either way, knowledge wins. And I really have to pause on this because this is just a masterclass in how modern science should be done. They pre-registered their entire analysis plan, which means they can't just cherry-pick the data later on. The tests are double-blind, and like we said, they're making everything public. The designs, the data, the code. This is all about being transparent, reproducible, and just plain rigorous. And just to really drive the point home, listen to how the researchers themselves put it. They are being incredibly careful and conservative here. They make it crystal clear they are not claiming to have invented warp drive or to have broken the laws of physics. They are testing one small, specific idea in the most responsible way they possibly can. And all of this leaves us with one last really fascinating question to chew on. If it's possible to build a proxy for the topology of spacetime on a little circuit board, what else could we test this way? This experiment isn't just about finding a twist. It's about opening the door to a whole new way of asking some of the biggest questions we have about the universe, right here on a lab bench. And that is an incredible thought to end on.